Right now, as you hear this, photons are hitting your eyes from a telescope floating 1.5 million kilometers away, the James Webb Space Telescope. It cost $10 billion. It took 30 years to build, and in the 2 years since it opened its mirror, it has seen things that should not exist. Not surprising things, not unexpected discoveries, things that violate the fundamental models of how the universe works, galaxies that formed impossibly fast after the Big Bang, structures so massive they shouldn't have had time to assemble, stars burning with chemical compositions that contradict everything we know about stellar evolution. Here is what the scientific community will not tell you directly. Every major cosmological discovery from James Webb has required scientists to append the phrase, "We don't understand why," to their papers. The standard model of cosmology, the lambda CDM model that has governed astrophysics for decades, is failing, not at the edges, at the core. This is not a story about a telescope finding pretty pictures of distant nebulae. This is a story about reality breaking down the moment we looked closely enough. About a machine designed to confirm our theories, instead shredding them. About the growing possibility that we have been catastrophically wrong about the history, structure, and fate of the universe. You wanted to understand the cosmos. James Webb showed you the cracks. The James Webb Space Telescope was not built to discover anomalies. It was built to see further back in time than any instrument in human history. To witness the first galaxies igniting in the primordial dark. To confirm, with exquisite precision, the timeline we had already written. Cosmologists knew the script. 13.8 billion years ago, the Big Bang. For 380,000 years, nothing but plasma. Then the cosmic microwave background, the afterglow we can still detect. Then darkness, the dark ages of the universe, when no stars yet burned. Then, slowly, over hundreds of millions of years, the first stars condensed from hydrogen clouds. Then, the first galaxies assembled from those stars. Small ones first. Dwarf galaxies containing maybe 10 million stars. Then, over billions of years, those dwarfs merged. Gravity pulled them together. They became the massive spiral and elliptical galaxies we see today. This was the model. This was lambda CDM, lambda cold dark matter cosmology. The universe expands. Dark energy drives that expansion. Dark matter provides the gravitational scaffolding. Normal matter, the stuff we can see, falls into that scaffolding and forms structure. Slowly, hierarchically, bottom up. Small things first, then bigger things. James Webb was supposed to photograph that process. To see those first small galaxies forming 600 million years after the Big Bang. To watch them grow over cosmic time. Instead, James Webb looked at the early universe and saw monsters. Within the first year of operation, astronomers pointed James Webb at a patch of sky that the Hubble Space Telescope had already surveyed. They were looking for galaxies at extreme distances, objects so far away that their light has been traveling toward us for over 13 billion years. Light that left those galaxies when the universe was only a few hundred million years old. What they found was Glass Z13, a galaxy detected at a redshift of 13.1. Redshift is how we measure distance in cosmology. The universe is expanding, so light from distant objects gets stretched, shifted toward the red end of the spectrum. The higher the redshift, the farther away the object, and the further back in time you are seeing. Glass Z13 existed when the universe was only 300 million years old. That alone was extraordinary. 300 million years is cosmically very young. But here is the problem that made astrophysicists go silent when they saw the data. Glass Z13 is enormous. It contains roughly 1 billion solar masses worth of stars. Do you understand what that means? Let me walk you through the catastrophe. Stars do not form instantly. A star like our Sun takes tens of millions of years to coalesce from a gas cloud, collapse under its own gravity, ignite fusion in its core. Massive stars form faster, maybe a few million years, but they also die faster, exploding as supernovae after only a few million years of life. To build a galaxy containing 1 billion stars, you need time. Lots of time. You need generations of stars to form, live, die, and enrich the interstellar medium with heavy elements so the next generation can form. According to our models, building a galaxy with 1 billion solar masses should take at least 500 million years, probably closer to a billion years. You need the first stars to form, which takes 100 million years. Then you need those stars to explode and spread heavy elements. Then you need the next generation of stars to form from that enriched gas. Then you need those stars to gravitationally bind together into a coherent galaxy. Then you need that galaxy to accrete more gas and form more stars. It is a slow, grinding process. Gravity works at the speed it works. Gas clouds collapse at the rate physics allows. There are no shortcuts. But Glass Z13 exists at 300 million years after the Big Bang. It is already mature. It is already massive. It is already burning with the light of a billion suns. And it should not be there. This is not one galaxy. This is not an outlier, a statistical fluke we can explain away. James Webb has now detected dozens of galaxies at redshifts above 10. Galaxies existing less than 500 million years after the Big Bang. And many of them are massive. Shockingly massive. Galaxies that should not have had time to assemble. There is a galaxy cataloged as CEERS 9356. It existed 450 million years after the Big Bang. It has a stellar mass of 10 billion solar masses. 10 billion stars worth of mass, formed in less than half a billion years. The models say this is impossible. Not unlikely. Impossible. There is not enough time in the history of the universe at that point for that much mass to have collapsed into stars. Another galaxy, CEERS 2746, also at extreme redshift, also absurdly massive. And another. And another. James Webb is finding them everywhere it looks. The early universe was not supposed to be populated with massive galaxies. It was supposed to be populated with small, dim proto-galaxies slowly growing over billions of years. But that is not what we see. We see a universe that was already mature, already structured, already filled with massive galaxies, impossibly early in cosmic history. This is called the impossible early galaxy problem. And it gets worse. Because these galaxies are not just massive, they are also too bright. When you look at the spectra of these early galaxies, the light signatures they emit, they are burning far more intensely than they should be. They are forming stars at rates that exceed what our models predict. Some of these galaxies are forming stars at a rate of hundreds of solar masses per year. Our Milky Way forms approximately 2 solar masses of new stars per year. These ancient galaxies are outproducing us by a factor of 100. Where is all that gas coming from? Star formation requires hydrogen. Lots of it. And in the early universe, gas should have been more diffuse, spread out, harder to collect into dense clouds where stars can form. But these galaxies are somehow funneling vast quantities of gas into their cores and igniting it into stars at a furious rate. The other problem is metallicity. In astronomy, any element heavier than helium is called a metal. Carbon, oxygen, iron, all metals. The first stars in the universe, the so-called population 3 stars, were made of pure hydrogen and helium because nothing else existed yet. Those stars lived, died, and exploded, seeding the universe with the first metals. The next generation of stars formed from gas that was slightly enriched with metals, and so on. Metallicity increases over time. The older the galaxy, the lower its metallicity should be. But some of these early galaxies that James Webb has observed show metallicity levels that are far too high for their age. They contain elements that should not exist yet, elements that require multiple generations of supernovae to produce. And yet, there they are, shining with the spectral signatures of carbon, oxygen, and even heavier elements, in galaxies that existed only a few 100 million years after the universe began. It is as if someone skipped several chapters in the story. As if the universe went from the Big Bang to mature, metal-rich galaxies without the intervening steps. Now, before you think this is simply a matter of scientists being surprised by nature, let me be clear about what is at stake. Lambda CDM is not just a theory. It is the foundation of cosmology. It explains the cosmic microwave background. It explains the large-scale structure of the universe. It explains how galaxies cluster. It predicts the distribution of dark matter. It has been tested and confirmed by decades of observations. It won Nobel Prizes, and these galaxies violate it. Not at the margins, at the core. If galaxies can form this fast, this early, then something is fundamentally wrong with our understanding of gravity, or dark matter, or the expansion rate of the universe, or all three. Some scientists have proposed solutions. Maybe star formation was more efficient in the early universe. Maybe the initial density fluctuations after the Big Bang were larger than we thought, allowing matter to collapse faster. Maybe dark matter behaves differently than we assumed. Maybe there were primordial black holes that seeded galaxy formation earlier than expected. But every proposed solution creates new problems. If star formation was more efficient early on, why? What mechanism would cause that? If density fluctuations were larger, why don't we see evidence of that in the cosmic microwave background? If dark matter behaves differently, how and why would it behave normally now but differently then? The models are breaking, not bending, breaking. And this is only the beginning. Because James Webb did not just find galaxies that are too old. It found galaxies that are too organized. When you look at nearby galaxies that are relatively close to us in the present-day universe, they have structure. Spiral galaxies have beautiful arms. Elliptical galaxies have smooth, organized distributions of stars. This structure takes time to develop. Galaxies start out chaotic, clumpy, irregular. Over billions of years, interactions with other galaxies, the influence of dark matter halos, and internal dynamics smooth them out. They become ordered, but James Webb is seeing highly structured galaxies at high redshift, galaxies with clear spiral arms, with organized cores, with symmetrical shapes. Galaxies that look mature, galaxies that look like they have been evolving for billions of years, except they have only existed for a few 100 million years. One galaxy in particular has baffled astronomers. It is called Jade's GSZ6 Cosmos. It is a barred spiral galaxy. A barred spiral is a galaxy where the spiral arms extend from the ends of a central bar-shaped structure of stars. Our Milky Way is a barred spiral. But barred spirals are thought to be the result of long-term dynamical evolution. The bar forms when the galaxy has been rotating for billions of years, and certain gravitational resonances kick in. It is a late-stage feature, a sign of maturity. Jade's GSZ6 Cosmos is seen at a redshift of 6.6. It existed less than 1 billion years after the Big Bang. And it already has a bar. Simulations say this should be impossible. There has not been enough time for the galaxy to rotate enough times to develop a bar. And yet, there it is, rotating, structured, barred, ancient. There is another structural anomaly that James Webb has revealed, and it concerns the very centers of these early galaxies. At the heart of almost every massive galaxy in the present-day universe sits a supermassive black hole. The Milky Way has one. It is called Sagittarius A star. It has a mass of approximately 4 million times the mass of our Sun. Andromeda has one with a mass of 100 million solar masses. M87, the giant elliptical galaxy famous for being the first black hole ever photographed, has a black hole weighing 6.5 billion solar masses. These black holes did not start out supermassive. Black holes form when massive stars collapse at the end of their lives. A stellar mass black hole might weigh 10 to 100 solar masses. To grow from 10 solar masses to 4 million solar masses, a black hole needs to eat. It needs to consume gas, dust, stars, and eating takes time. When a black hole feeds, matter does not simply fall straight in. It forms an accretion disk, a swirling vortex of material spiraling inward. Friction in the disk heats the gas to millions of degrees, causing it to emit X-rays and visible light. This is why actively feeding black holes are some of the brightest objects in the universe. We call them quasars, or active galactic nuclei. But there is a limit to how fast a black hole can eat. It is called the Eddington limit. When a black hole feeds, the matter falling in releases radiation. That radiation pushes outward. If the black hole tries to eat too fast, the radiation pressure becomes so strong that it blows away the infalling matter. The black hole chokes on its own light. The Eddington limit sets a maximum growth rate. A black hole can roughly double its mass every 50 million years if it feeds continuously at the Eddington limit. So, if you start with a 10 solar mass black hole and let it feed continuously at maximum rate, after 50 million years you have a 20 solar mass black hole. After 100 million years, 40 solar masses. After 500 million years you might have a few thousand solar masses. After 1 billion years, maybe a few 100,000 solar masses. To grow a black hole to 1 million solar masses, starting from a stellar mass seed, should take at least 1 billion years of continuous feeding at maximum rate. To grow 1 to 1 billion solar masses should take longer, much longer. But James Webb has found quasars, actively feeding supermassive black holes at redshifts above 7. These quasars existed less than 700 million years after the Big Bang. And they are not small. They are already supermassive. Some have masses exceeding 1 billion solar masses. One quasar in particular has horrified cosmologists. It is designated J0313-1806. It was discovered at a redshift of 7.64, meaning it existed when the universe was only 670 million years old. The black hole powering this quasar has a mass of approximately 1.6 billion solar masses. Let me be very clear about the problem. If you start with a black hole seed of 100 solar masses, which is already generous, and let it feed at the Eddington limit continuously without stopping, it would take approximately 1.2 billion years to reach 1.6 billion solar masses. But the universe at the time of this quasar was only 670 million years old. The black hole is older than the universe should have allowed it to become. The only way to explain this is if the black hole started much more massive, not 100 solar masses, maybe 100,000 solar masses, maybe 1 million solar masses. But how do you form a black hole that massive in the first place? Stellar collapse gives you 10 to 100 solar masses. Direct collapse of massive gas clouds could theoretically give you 100,000 solar masses. But that requires very specific conditions. Pristine gas. No turbulence. No fragmentation. And even then, it is speculative. Or the black hole fed faster than the Eddington limit allows. Some mechanism we do not understand allowed it to eat at super Eddington rates, consuming matter faster than radiation pressure should permit. But we have no observations of black holes doing this at such extreme rates, and we have no theoretical framework that would allow it. Or there is a third option. The black hole formed through some exotic mechanism we have not discovered. Primordial black holes formed in the first seconds after the Big Bang, collisions of dark matter producing black holes directly, some process in the quantum foam of space-time itself. But all of these are speculation, desperation, attempts to fit an observation into a framework that cannot contain it. And J0313-1806 is not alone. James Webb has found multiple quasars at redshifts above 7, multiple supermassive black holes that should not exist yet. The early universe is populated with black holes that are impossibly old. There is a relationship in astrophysics called the M-sigma relation. It describes the connection between the mass of a supermassive black hole and the velocity dispersion of stars in the galaxy's central bulge. Basically, bigger black holes live in bigger galaxies. This makes sense. The black hole and the galaxy grow together, they co-evolve. As the galaxy merges with other galaxies and grows more massive, the black hole feeds and grows more massive. They are linked. But the M-sigma relation is based on observations of galaxies in the local, present-day universe. Galaxies that have had 13 billion years to evolve. When James Webb looks at high redshift galaxies, at galaxies in the early universe, the M-sigma relation appears to be different. The black holes are too massive for their host galaxies. They are overmassive. As if the black hole grew faster than the galaxy, or formed earlier, or through some process that did not require a large galaxy to already exist. This creates a causality problem. Did the black hole form first and then attract gas that became the galaxy? Or did the galaxy form first and then the black hole grew at its center? Our models assume the latter, but the observations suggest the former. And if supermassive black holes form before galaxies, then what formed them? What mechanism in the chaotic plasma of the early universe could create billion solar mass black holes before stars had even properly ignited? Some theorists have proposed that supermassive black holes formed directly from the collapse of massive dark matter halos in the early universe. Dark matter does not interact with light, but it does interact with gravity. In regions where dark matter was especially dense, it could have collapsed into a massive structure. And normal matter falling into that structure could have formed a supermassive black hole directly, skipping the star formation step entirely. This is called direct collapse black hole formation. It is elegant. It solves the timing problem, but it requires very specific initial conditions. The gas needs to be very pristine, very hot, and very dense, and we have no direct evidence that this process actually occurs. It is a mathematical possibility, not an observed phenomenon. Until James Webb, we could ignore it. We could say, maybe this happens, but it is rare. Now, we cannot ignore it. Because if these early supermassive black holes are common, if James Webb is finding them everywhere it looks, then direct collapse might not be rare. It might be the primary way supermassive black holes formed in the early universe, which means our entire model of galaxy black hole coevolution is wrong. Let me take you deeper into another anomaly, the problem of cosmic structure. When cosmologists map the universe, they do not just map individual galaxies. They map the large-scale structure. Galaxies are not distributed randomly in space. They cluster. They form groups. Those groups form clusters. Those clusters form superclusters. And those superclusters are arranged along vast filaments, cosmic threads of matter stretching across hundreds of millions of light-years, surrounding enormous voids where very few galaxies exist. This is the cosmic web, and it formed through gravity. After the Big Bang, matter was distributed almost uniformly throughout space, but not perfectly. There were tiny density fluctuations, regions where matter was slightly more dense or slightly less dense. Gravity amplified these fluctuations. Denser regions attracted more matter, becoming even denser. Over hundreds of millions of years, these regions collapsed into the first galaxies. Over billions of years, those galaxies clustered together, forming the large-scale structure we see today. The key word is billions. Large-scale structure takes time to develop. Gravity is powerful, but it works slowly. To pull galaxies together across millions of light-years requires time. Our simulations, our computer models of structure formation, predict how long this should take. We input the initial conditions from the cosmic microwave background, we input the density of dark matter, we input the expansion rate of the universe, we let the simulation run forward in time. And the simulation produces a cosmic web that looks remarkably like the one we observe today. Filaments, voids, clusters. It all matches. But the simulations also predict how the cosmic web looked in the past. And according to the simulations, large-scale structure should have been much less developed in the early universe. At redshift 5, about 12 billion years ago, clusters should have been smaller, filaments should have been thinner, voids should have been less empty. The cosmic web should have been more homogeneous, less organized. James Webb has looked at the universe at redshift 5, and the cosmic web looks fully formed. Filaments already stretching across vast distances, voids already carved out, clusters already dense with galaxies. Structure that should have taken another few billion years to develop is already there. One particular structure has caused alarm. It is a proto-supercluster detected at redshift 7.9. A concentration of galaxies spanning approximately 20 million light-years. This structure existed only 650 million years after the Big Bang. At that point in cosmic history, according to lambda CDM, galaxies should barely be clustering at all. The largest structures should be maybe a few million light-years across. But here is a proto-supercluster, a precursor to the massive superclusters we see today, already assembled. How did gravity pull all those galaxies together so quickly? The math does not work. The time does not work. It is as if someone built a city overnight. And this structure is not unique. James Webb is finding large-scale structure at high redshift everywhere. The universe was already organized, already webbed, already clustered, impossibly early. There is a phrase that keeps appearing in the scientific papers analyzing James Webb data. Tension with lambda CDM. Tension. As if the model is a rubber band stretched too far. As if it is about to snap. Let me tell you what tension means in this context. It means the observations do not match the predictions. Not slightly, not within error bars, significantly. Irreconcilably. When Hubble discovered the first high redshift galaxies in the 1990s, there were surprises. Galaxies looked different at high redshift, more irregular, more active, but nothing that broke the model. Everything could be explained within lambda CDM with some adjustments. James Webb is not delivering adjustments, it is delivering contradictions. There is now serious discussion among cosmologists about whether lambda CDM needs to be abandoned. Not modified, abandoned, replaced with a new framework that can accommodate these observations. But here is the problem. Lambda CDM works everywhere else. It explains the cosmic microwave background perfectly. The tiny temperature fluctuations in the CMB match lambda CDM predictions to extraordinary precision. It explains the abundance of light elements, hydrogen and helium, produced in the first minutes after the Big Bang. It explains the rotation curves of galaxies. The way stars orbit too fast to be held by visible matter alone, requiring dark matter. It explains the accelerating expansion of the universe, requiring dark energy. Lambda CDM is not some speculative fringe theory. It is the result of decades of observations, tested and confirmed over and over. And now, James Webb is saying it is wrong. But wrong about what? Wrong about gravity? Wrong about dark matter? Wrong about the initial conditions of the universe? No one knows. And that is the terror. When your foundational model breaks, you do not just lose a theory, you lose your framework for interpreting reality. Every observation becomes ambiguous. Every measurement becomes suspect. You are floating in the dark, unsure which direction is up. Some cosmologists have proposed modifying the initial conditions. Maybe the density fluctuations in the early universe were larger than we thought. This would allow structure to form faster. But if the fluctuations were larger, we should see evidence of that in the cosmic microwave background. We do not. The CMB shows very uniform, very small fluctuations, exactly as lambda CDM predicts. Others have proposed modifying dark matter. Maybe dark matter interacts with itself in ways we have not accounted for. Maybe it clumps more efficiently. Maybe it has properties we have not discovered. But dark matter works perfectly in our local universe. It explains galaxy rotation curves. It explains gravitational lensing. Why would it behave differently in the early universe? Still others have proposed modifying gravity itself. Maybe Einstein's general relativity is incomplete. Maybe at extreme scales or extreme conditions, gravity behaves differently. This is called modified Newtonian dynamics, or MOND. But MOND has its own problems. It cannot explain the cosmic microwave background. It cannot explain gravitational lensing observations without resorting to additional assumptions. Every proposed solution creates new problems, and meanwhile James Webb keeps finding more galaxies, more black holes, more structure. All of it too early, too massive, too organized. The telescope was supposed to confirm the story. Instead, it is shredding the book. There is another category of anomaly that James Webb has uncovered, and it strikes at an even more fundamental question. Not just when galaxies formed, or how fast black holes grew, but what the universe is made of. Spectroscopy is the art of breaking light into its component wavelengths. When you pass sunlight through a prism, you get a rainbow. Each color corresponds to a specific wavelength of light. But if you look closely at that rainbow, you will see dark lines, absorption lines. These lines appear because specific elements in the sun's atmosphere absorb specific wavelengths of light. Hydrogen absorbs at certain wavelengths, helium at others, iron, carbon, oxygen. Every element has a unique spectral fingerprint. By analyzing the spectrum of a distant galaxy, we can determine what elements it contains. We can measure the ratio of hydrogen to helium. We can detect metals, the heavy elements produced in stars. We can trace the chemical evolution of the universe. The story we have told goes like this. The Big Bang produced hydrogen and helium, almost nothing else. Trace amounts of lithium. That is it. The first stars, population 3 stars, formed from this pristine gas. They were massive, hot, and short-lived. When they exploded as supernovae, they scattered the first metals into space. carbon, oxygen, nitrogen, iron. The next generation of stars, population 2 stars, formed from gas that was slightly enriched with these metals. They lived, died, and enriched the gas further. Eventually, population 1 stars like our Sun formed from gas that was approximately 2% metals. This process is called chemical evolution, and it takes time, billions of years. Each generation of stars adds more metals. The metallicity of the universe increases slowly, steadily, over cosmic history. James Webb has measured the spectra of some of these impossibly early galaxies. And the metallicity is wrong. Some of these galaxies show metallicity levels far higher than they should. Oxygen lines that are too strong. Carbon lines that are too strong. Nitrogen. Silicon. Elements that require not just one generation of supernovae, but multiple generations. Elements that should not exist in such abundance only a few 100 million years after the Big Bang. One galaxy in particular, observed at redshift 8.5, shows oxygen abundance approximately 30% of solar levels. 30%. Our Sun formed 4.6 billion years ago from gas that had been enriched by billions of years of stellar evolution. This galaxy existed only 550 million years after the Big Bang, and it already has 1/3 the oxygen abundance of our Sun. How? The only way to produce that much oxygen is through massive stars. Stars at least 8 times the mass of the Sun. These stars burn through their fuel quickly, fuse elements up to iron in their cores, and then explode, scattering those elements into space. But massive stars are rare. They make up only a small fraction of all stars, and they die quickly, within a few million years. To enrich a galaxy to 30% solar oxygen levels, you need multiple generations of massive stars. You need the first generation to explode, enriching the gas. You need the second generation to form from that enriched gas, burn and explode. You need the third generation to form and explode. Each cycle takes tens of millions of years. And you need this to happen not just in one region of the galaxy, but throughout the galaxy, mixing the metals into the gas so that the whole galaxy becomes enriched. This process should take at least 500 million years, probably closer to 1 billion years. But this galaxy has done it in half that time. The enrichment is too fast. The metallicity is too high. The timeline does not close. Some of these galaxies also show unusual abundance ratios. The ratio of carbon to oxygen. The ratio of nitrogen to oxygen. These ratios tell us about the types of stars that produce the metals. Different types of supernovae produce different ratios. In our local universe, in galaxies that have had billions of years to evolve, the abundance ratios follow predictable patterns. The patterns match our models of stellar nucleosynthesis. We understand which stars produce which elements. We can trace the chemical history of a galaxy by measuring these ratios. But some of the high redshift galaxies observed by James Webb show abundance ratios that do not match any known stellar population. Ratios that cannot be explained by normal supernovae. Ratios that suggest either a completely different mix of star types than we have ever observed, or some exotic nucleosynthesis process we do not understand. One galaxy shows an extremely high nitrogen to oxygen ratio. Nitrogen is primarily produced in intermediate mass stars, stars a few times the mass of the Sun. These stars live longer than massive stars, hundreds of millions of years. They enrich the gas slowly. But this galaxy, existing less than 700 million years after the Big Bang, has nitrogen levels that suggest intermediate mass stars have already lived and died. Stars that should not have had time to complete their life cycles. Unless the initial mass function was different in the early universe, the initial mass function, or IMF, describes the distribution of stellar masses when stars form. In the present-day universe, most stars are low mass. Red dwarfs. Stars less than half the mass of the Sun. Massive stars are rare. The IMF is said to be bottom-heavy. But what if, in the early universe, the IMF was top-heavy? What if most stars that formed were massive stars? This would produce metals faster. More supernovae. More enrichment in less time. It would solve the metallicity problem. But it creates a new problem. Why would the IMF be different? What physical mechanism would cause preferentially massive stars to form in the early universe but not now? The physics of star formation should be the same. Gas collapses under gravity. Fragments form cores. Cores ignite fusion. The process is universal. Some theorists suggest that the absence of metals itself causes the IMF to be top-heavy. Metals act as coolants in collapsing gas clouds. They radiate energy away, allowing the cloud to collapse into smaller fragments, which become smaller stars. Without metals, the gas cannot cool as efficiently. It collapses into larger, hotter cores, which become more massive stars. This is plausible. But if it were true, we should see evidence of it in the oldest stars in our own galaxy. Population 2 stars with very low metallicity should show signs of having formed in an environment dominated by massive stars. They do not. The oldest stars in the Milky Way halo have abundance patterns consistent with a normal IMF. So either the early universe was fundamentally different in ways we do not understand, or our models of nucleosynthesis are incomplete. Or James Webb is detecting some contaminant, some foreground object, some artifact that is mimicking these signals. Except we have checked. Multiple teams, multiple instruments, multiple methods. The signals are real, the metallicities are real, the galaxies are real, and then there is the Hubble tension. This is not strictly a James Webb discovery, but James Webb has made it worse. The Hubble tension refers to a discrepancy in measurements of the Hubble constant, the rate at which the universe is expanding. There are two primary methods for measuring the Hubble constant. The first method uses the cosmic microwave background. We measure the temperature fluctuations in the CMB, plug them into lambda CDM, and calculate what the expansion rate should be today. This method gives a value of approximately 67 kilometers per second per megaparsec. The second method uses distance measurements to nearby galaxies. We observe Cepheid variable stars, pulsating stars whose brightness varies in a predictable way. The period of pulsation is related to the star's intrinsic luminosity. By measuring how bright the Cepheid appears, we can calculate its distance. Once we know the distance, we can measure how fast the galaxy is receding by looking at its redshift. Distance divided by velocity gives us the Hubble constant. This method gives a value of approximately 73 kilometers per second per megaparsec. 67 versus 73. That is a 9% discrepancy. In astronomy, where error bars are often large, 9% might not sound like much. But these measurements are precise. Multiple teams, multiple methods, multiple cross-checks. The error bars do not overlap. One of them is wrong, or both of them are wrong, or the universe is doing something we do not understand. If the local measurement is correct, if the Hubble constant is 73, then the universe is expanding faster than lambda CDM predicts, which means either the model is wrong, or there is some additional component of dark energy we have not accounted for, or the universe underwent some transition in its expansion history that we do not understand. If the CMB measurement is correct, if the Hubble constant is 67, then there is something systematically wrong with our local distance measurements. Some unknown bias affecting Cepheids or supernovae or gravitational lensing. But we have checked over and over. the measurements appear sound. James Webb was supposed to help resolve this tension. It can observe Cepheids in galaxies farther away than Hubble could reach. More Cepheids, better measurements, more precise distances. The hope was that James Webb would either confirm the 73 value, proving the local measurement correct, or find some error that brings the value down to 67, confirming the CMB measurement. Instead, James Webb has confirmed the 73 value. With even greater precision, the local measurement is not wrong. The universe really is expanding 9% faster than lambda CDM predicts. This means the model is broken. Not slightly miscalibrated. Fundamentally broken. Either dark energy is not constant, or there is a new component of dark energy, or general relativity is incomplete, or the universe is not homogeneous on large scales as we assume, or something else, something we have not even conceived of, is influencing the expansion. And if the expansion rate is wrong, then our distance measurements are wrong, which means our age estimates are wrong, which means the timeline of cosmic history is wrong, which means all of the constraints we have placed on galaxy formation, on structure formation, on black hole growth, all of it is built on a faulty foundation. Some cosmologists have proposed early dark energy, a component of dark energy that was present in the early universe but has since diluted away. This would increase the early expansion rate, bringing the CMB prediction in line with the local measurement. But early dark energy requires fine-tuning. Why would dark energy behave one way early on and differently now? What mechanism would cause it to dilute? Others have proposed modifications to general relativity. Maybe gravity behaves differently on cosmological scales. Maybe the equations need additional terms. But every modification that fixes the Hubble tension breaks something else. Galaxy rotation curves, gravitational lensing, the CMB power spectrum. General relativity is too well tested. You cannot tweak it without consequences. Still, others have proposed that we are living in a locally underdense region of the universe, a cosmic void. If we are in a void, the local expansion rate could appear faster than the cosmic average. This would reconcile the measurements without breaking the model. But observations of the cosmic microwave background and large-scale structure suggest the universe is homogeneous on large scales. We do not see evidence of a large void centered on us. And even if we did, that would be its own kind of problem, because why would we happen to live in a special location? The Copernican principle, the foundation of modern cosmology, states that we do not occupy a special place in the universe. We are typical observers in a typical location. If we are in a void, we are not typical. And if we are not typical, then what does that mean for all of our other observations? How much of what we think we know is biased by our unusual location? The Hubble tension is not going away. It is getting worse. And James Webb is confirming it. The universe is expanding faster than it should, and we do not know why. Now let me take you to the edge of another impossibility. The chemistry of exoplanet atmospheres. James Webb was not designed only to observe distant galaxies. It was also designed to study exoplanets, planets orbiting stars other than our Sun. Specifically, it was designed to study their atmospheres. When an exoplanet passes in front of its star, a tiny fraction of the star's light passes through the planet's atmosphere before reaching us. By analyzing that light by breaking it into a spectrum, we can detect the chemical composition of the atmosphere: water vapor, carbon dioxide, methane, oxygen. One of the holy grails of exoplanet science is detecting a biosignature, a chemical that indicates the presence of life. On Earth, oxygen is a biosignature. Oxygen is highly reactive. It does not persist in an atmosphere unless something is constantly producing it. On Earth, that something is photosynthesis. Plants, algae, cyanobacteria, life. If we detected oxygen in the atmosphere of an Earth-like exoplanet, it would be strong evidence of life. James Webb has now observed the atmospheres of dozens of exoplanets, and the chemistry is strange. One exoplanet, K2-18b, is approximately 8.6 times the mass of Earth. It orbits a red dwarf star about 120 light-years away. It is located in the habitable zone, the region where liquid water could exist on the surface. James Webb observed K2-18b during a transit and detected water vapor. Not surprising. Water is common in the universe. But James Webb also detected dimethyl sulfide. Dimethyl sulfide, or DMS, is a molecule that, on Earth, is produced almost exclusively by biological processes. Specifically, by phytoplankton in the ocean. When phytoplankton die and decay, they release DMS. It is one of the reasons the ocean has a distinct smell. DMS is not stable in an atmosphere. It breaks down quickly under ultraviolet light. For DMS to persist, something must be constantly producing it. The detection of DMS on K2-18b is tentative. It requires confirmation. But if it is real, if DMS is truly present in the atmosphere of this exoplanet, then either there is life on K2-18b or there is some abiotic, non-biological process producing DMS that we do not know about. Both possibilities are extraordinary. If there is life, then life is common. We found it on the first potentially habitable exoplanet we looked at closely. If there is an abiotic process, then our understanding of atmospheric chemistry is incomplete. Another exoplanet, WASP-39b, is a hot Jupiter, a gas giant orbiting very close to its star. Its atmosphere should be hydrogen and helium, with traces of water and carbon monoxide. James Webb detected all of that. But it also detected sulfur dioxide in unexpectedly high concentrations. Sulfur dioxide on Earth is produced by volcanic activity, but WASP-39b is a gas giant. It has no surface, no volcanoes. Where is the sulfur dioxide coming from? The leading theory is photochemistry. Ultraviolet light from the star is breaking apart molecules in the atmosphere and reassembling them into sulfur dioxide. But the amount of sulfur dioxide detected exceeds what photochemistry models predict. Either the models are wrong, or there is some additional source of sulfur, or the atmospheric dynamics are more complex than we thought. James Webb has also observed the atmosphere of an exoplanet called GJ1214b. This is a rocky planet, slightly larger than Earth, orbiting a red dwarf star 40 light-years away. Its atmosphere should be thin, maybe carbon dioxide and nitrogen, similar to Venus or Mars. Instead, James Webb detected a thick hydrogen atmosphere. But hydrogen is light. It should have escaped from a rocky planet this size over millions of years. The fact that it still has hydrogen suggests the planet is either much younger than we thought, or it is continuously replenishing its hydrogen somehow. One possibility is outgassing. Hydrogen trapped in the planet's interior is being released through volcanic activity. But that would require the planet to be geologically active, which requires internal heat. Rocky planets lose internal heat over time. A planet this small should have cooled and solidified by now. Another possibility is that the planet is being bombarded by comets, icy bodies delivering hydrogen. But bombardment should have declined long ago. The solar system around GJ1214 should have cleared out its comets billions of years ago, or the planet is not rocky. Maybe we misidentified it. Maybe it is a small gas giant, a mini Neptune, not a rocky super-Earth. But its mass and radius suggest it is rocky. The density is too high for a gas giant. So what is it? These atmospheric anomalies are piling up, planet after planet showing unexpected chemistry, molecules that should not be there, abundances that do not match models. It is as if every time we look closely at an exoplanet, we find something wrong. And this brings us to a deeper question. If our models of exoplanet atmospheres are this broken, how confident can we be in our models of anything else? Stellar atmospheres. Galactic gas. The interstellar medium. If we cannot predict the chemistry of a planet orbiting a nearby star, how can we claim to understand the chemistry of a galaxy 13 billion light-years away? There is another class of object that James Webb has discovered, and no one knows what they are. They are called little red dots. When astronomers first started analyzing James Webb Deep Field images, looking for distant galaxies, they found these peculiar objects. Small, compact, extremely red. At first, they seemed like ordinary high redshift galaxies. Galaxies that are very far away appear red because their light has been stretched by the expansion of the universe. The more distant the galaxy, the redder it appears. This is basic cosmology. But when spectroscopy was performed on these little red dots, the data made no sense. The spectra showed broad emission lines, the signature of an active galactic nucleus, a feeding supermassive black hole. But the objects were too compact to be galaxies. Their size was measured in hundreds of light-years, not tens of thousands of light-years like normal galaxies. Some of these little red dots have luminosities equivalent to 1 billion suns packed into a region the size of our solar neighborhood. That power density is consistent with a quasar. But quasars exist at the centers of massive galaxies. They are surrounded by stars, billions of stars. The little red dots show no evidence of a surrounding galaxy. They are just the nucleus, just the black hole and its immediate environment. But where is the galaxy? One possibility is that the galaxy is there, but hidden, obscured by dust. Dust absorbs visible light and re-emits it in the infrared. James Webb sees in the infrared, so it should be able to see through dust. But if the dust is extremely thick, optically thick, it might block even infrared light. The galaxy could be buried. But if that is the case, the amount of dust required is staggering. Far more dust than any galaxy we have ever observed. And where would that dust come from? Dust is made of heavy elements: carbon, silicon, oxygen. Elements produced by stars. But if these objects exist at high redshift, in the early universe, there should not be enough time for enough stars to have lived and died to produce that much dust. Another possibility is that these are not galaxies at all. They are rogue black holes. Black holes that formed in the early universe without a surrounding galaxy. Primordial black holes. But if primordial black holes exist, where did they come from? How do you form a black hole without a star? Direct collapse from a gas cloud? Quantum fluctuations in the Big Bang itself? Exotic physics we have not discovered? Or these are not black holes, they are something else. Some exotic object we have never encountered. A new category of astronomical phenomenon. One research team suggested they might be dark stars. Not stars made of normal matter, but stars powered by dark matter annihilation. When dark matter particles collide with their antiparticles, they annihilate, releasing energy. In regions of the early universe where dark matter was extremely dense, this annihilation energy could have heated a cloud of gas, causing it to shine. A dark star would be extremely massive, extremely luminous, and extremely red because of the high dust content. But dark stars are purely theoretical. No one has ever observed one. And the physics requires very specific conditions: a dense, dark matter halo, a pristine gas cloud, no contamination by metals, and even then, the dark star would only last a few million years before collapsing into a black hole. Another team suggested the little red dots are massive protostars, stars still in the process of forming. Protostars are embedded in dense cocoons of gas and dust. They are highly obscured. They appear red. But protostars are small, a few solar masses at most. The little red dots are too luminous to be single protostars, unless they are clusters of protostars. Thousands of stars forming simultaneously in a very compact region. But even that has problems. Star formation is self-limiting. When massive stars form, they emit intense radiation that heats and disperses the surrounding gas, shutting down further star formation. To pack thousands of protostars into a region hundreds of light years across, you would need to overcome this radiation feedback, and we have no mechanism that would allow that. So we are left with a mystery: little red dots, dozens of them, scattered across the high redshift universe, too bright to be galaxies, too compact to be quasars, too obscured to identify. They exist, James Webb sees them, but we do not know what they are. And this is not a trivial mystery. These objects are numerous. They are not rare flukes, they are common. Which means whatever process created them is a major component of the early universe. A process we have not accounted for in our models. A process that could be producing significant amounts of light, energy, and possibly even heavy elements, affecting the entire evolution of the cosmos. If these are black holes without galaxies, then black holes can form without galaxies, which breaks the M-sigma relation and rewrites our understanding of galaxy formation. If these are dark stars, then dark matter interacts in ways we have not detected, which breaks particle physics. If these are something else entirely, then we are missing an entire category of astrophysical objects. Now let me take you into the problem of reionization. This is one of the most important epochs in cosmic history, and James Webb is showing us that we have it completely wrong. After the Big Bang, the universe was hot and ionized. All the electrons were stripped from their atoms. The universe was a plasma, but as the universe expanded and cooled, electrons recombined with protons to form neutral hydrogen. This happened about 380,000 years after the Big Bang, and it is called recombination. For the next few 100 million years, the universe was dark, filled with neutral hydrogen. No stars had formed yet. This is called the Dark Ages. Then, the first stars ignited. These first stars were massive and hot. They emitted intense ultraviolet radiation. This radiation was energetic enough to ionize hydrogen, stripping electrons from atoms again. As more stars formed, they ionized more hydrogen. Bubbles of ionized gas expanded around the first galaxies. Eventually, these bubbles overlapped, and the entire universe became ionized again. This is called the epoch of reionization. It is one of the major phase transitions in cosmic history. The universe went from neutral to ionized, from dark to transparent. According to our models, reionization should have taken a long time, hundreds of millions of years. Starting around 200 million years after the Big Bang and completing around 1 billion years after the Big Bang. The process should have been gradual, a slow percolation as more and more stars formed and ionized more and more hydrogen. But observations suggest reionization happened faster, much faster. By the time the universe was 600 million years old, it was already mostly ionized. That is far too early. There should not have been enough stars to ionize the universe that quickly. And James Webb has made this problem worse, because James Webb can see the galaxies that existed during reionization. It can count them. It can measure their star formation rates. And when you add up all the ultraviolet light produced by all the galaxies James Webb has detected, it is not enough. Not even close. To ionize the universe, you need approximately 1 ultraviolet photon for every hydrogen atom in intergalactic space. Actually, you need more than 1, because some photons get absorbed by dust or by hydrogen atoms that immediately recombine. You need approximately 10 photons per hydrogen atom. When you calculate the total ultraviolet luminosity of all the galaxies detected by James Webb at high redshift, you get enough photons to ionize maybe 20% of the universe. Not 100%, 20%. Where are the other 80% of the photons coming from? One possibility is that there are many more galaxies than James Webb can detect. Faint dwarf galaxies. Galaxies with only a few million stars. These would be too dim for James Webb to see, but collectively they could produce enough ultraviolet light to ionize the universe. But we can estimate how many faint galaxies should exist. We can extrapolate from the galaxies we can see. And even with generous assumptions, even if we assume there are 10 times more faint galaxies than we can detect, it is still not enough. The photon budget does not close. Another possibility is that the first stars were more efficient at ionizing hydrogen than we thought. Maybe they were more massive, more luminous, more energetic, producing more ultraviolet photons per unit mass. This is plausible. The first stars formed from pristine gas with no metals. Without metals to cool the gas, the collapsing clouds would have been hotter, forming more massive stars. But this creates the same problem we encountered before. If the first stars were all massive, where are the abundance patterns they should have left behind? Massive stars produce different elemental ratios than normal stars. We should see evidence of this in the oldest stars in our galaxy. We do not. A third possibility is that there is another source of ionizing radiation. Not stars, something else. Quasars. Actively feeding black holes. Quasars emit enormous amounts of ultraviolet light. A single quasar can ionize a region millions of light years across. But quasars are rare. James Webb has detected some quasars at high redshift, but not enough to ionize the universe. You would need millions of quasars. Millions of supermassive black holes actively feeding during the epoch of reionization, and we do not see them. Or there is an exotic source, decaying dark matter. If dark matter particles are unstable and decay into normal particles, they would release energy. If this energy is in the form of ultraviolet photons, it could ionize hydrogen. But dark matter is supposed to be stable. That is why it is still around. If it decayed, there would be less of it now than in the early universe. And observations suggest dark matter density has remained constant. Or the universe reionized differently than we thought. Not gradually. Not through percolating bubbles. But suddenly. All at once. Some catastrophic event flooded the universe with radiation. A massive burst of star formation, a wave of supernova, a phase transition in the vacuum of space itself. But what would trigger such an event? And why do we not see evidence of it? A sudden reionization would leave specific signatures in the distribution of hydrogen. It would affect the formation of the first galaxies. It would alter the cosmic microwave background. We see none of these signatures. So we are stuck. The universe reionized too early. The galaxies we observe are not producing enough photons to ionize it. And we do not know what else could have done it. There is another timeline problem that James Webb has revealed. The problem of dust. Dust is made of solid particles, grains of carbon, silicates, metals. These grains form in the atmospheres of dying stars, specifically red giant stars and supernovae. When a star dies, it ejects material into space. That material cools and condenses into dust grains. Over billions of years, the interstellar medium becomes enriched with dust. Dust is crucial for star formation. Dust grains act as catalysts for the formation of molecular hydrogen. Hydrogen atoms land on the surface of a dust grain, meet another hydrogen atom, bond together, and form H2, molecular hydrogen. Molecular hydrogen is the fuel for star formation. Without dust, star formation would be far less efficient. In the early universe, there should have been very little dust. The first stars had not yet died. No red giants, no supernovae, no dust production. Star formation should have been dust-free, relying on other cooling mechanisms. But James Webb is detecting significant amounts of dust in early galaxies. Galaxies at redshift 7, redshift 8, redshift 9. Galaxies that should be pristine, metal-poor, and dust-free. Instead, they are dusty, obscured by dust. Glowing in the infrared because the dust is absorbing visible light and re-emitting it. One galaxy, detected at redshift 8.5, has a dust mass equivalent to 10 million times the mass of the Sun, 10 million solar masses of dust. In a galaxy that has only existed for 550 million years, to produce that much dust, you need millions of stars to live, die, and eject material. You need supernovae, lots of them, and you need time for the dust to form and mix into the interstellar medium. According to models, producing 10 million solar masses of dust should take at least 1 billion years. Probably longer. But this galaxy has done it in half that time. The dust is there, James Webb sees it, but the timeline does not work. Some theorists have proposed that dust forms more efficiently in the early universe. Maybe supernovae in metal-poor environments produce more dust. Maybe the lack of metals allows dust grains to grow larger, forming faster. But observations of nearby metal-poor galaxies do not support this. Dust production seems consistent across different metallicity environments. Others have proposed that dust forms through different mechanisms in the early universe. Not in stellar atmospheres, but in the interstellar medium itself. Gas phase chemistry. Molecules colliding in dense clouds, forming grains directly. But this process is slow, and it requires dense clouds, which require gravity, which requires time to assemble. Or the dust is primordial, formed in the Big Bang itself. But the Big Bang only produced hydrogen and helium. No carbon, no silicon, no metals, no dust. So where is the dust coming from? How did it form so quickly? And if dust is abundant in the early universe, does that change how stars form? Does it change the initial mass function? Does it alter the chemical evolution of galaxies? Every answer leads to more questions. Every observation deepens the mystery. Let me take you now to an anomaly that strikes at the heart of stellar evolution: the problem of stellar populations. Stars are classified into populations based on their metallicity. Population 3 stars are the first stars, formed from pristine hydrogen and helium, 0 metals. Population 2 stars are the next generation, formed from gas enriched by population 3 supernovae, low metallicity. Population 1 stars are the current generation, like our Sun, high metallicity, approximately 2% metals. We have never observed a population 3 star. They are all dead. They lived fast and died young. But we should see their remnants. Specifically, we should see the stars that formed from the gas they enriched. Population 2 stars with extremely low metallicity, but not 0. These stars should exist in the halos of galaxies, in globular clusters, in the ancient structures that formed first. We have found some of these stars in the Milky Way. Stars with metallicities 1/10,000th of solar, 100,000th. They are rare, but they exist. And their abundance patterns tell us about the supernovae that enriched them, about the first stars that died and seeded the universe with metals. But there is a problem. The abundance patterns do not match our models. Specifically, the ratio of certain elements is wrong. When a massive star explodes as a supernova, it produces specific ratios of elements depending on its mass and the type of explosion. A star 20 times the mass of the Sun produces one ratio. A star 100 times the mass of the Sun produces a different ratio. By measuring the ratios in low metallicity stars, we can infer the masses of the first stars that enriched them. The problem is that the observed ratios do not match any single type of supernova. They are a mix, as if the gas was enriched by multiple types of supernovae. But that requires multiple generations of stars. And if you need multiple generations, you need time. More time than should be available in the early universe. James Webb is now detecting galaxies at such high redshifts that we can measure their stellar populations directly. And the populations are weird. One galaxy at redshift 8 shows spectral features consistent with both young, hot stars and old, cool stars. Young stars produce ultraviolet light. Old stars produce red light. This galaxy is producing both, which means it contains stars of different ages. But if the galaxy is only 500 million years old, and the oldest stars live for billions of years, then all the stars in the galaxy should be young. There should not be old stars yet, unless the galaxy formed in a burst. All its stars formed very early, within the first 100 million years. Then star formation shut off. The massive stars died quickly, leaving behind old, low-mass stars. But what would shut off star formation? Gas needs to be removed or heated. Supernova feedback could do it, but that many supernovae would also enrich the gas with metals. And this galaxy has low metallicity. Another galaxy shows a spectrum dominated by red supergiants. Red supergiants are evolved massive stars. They start as hot, blue stars. They burn through their hydrogen fuel. They swell into red giants. Then they explode as supernovae. The red supergiant phase lasts only a few million years. It is a brief moment in a star's life. For a galaxy to have a spectrum dominated by red supergiants, the timing has to be perfect. The massive stars all need to be in the red supergiant phase simultaneously. This happens if all the stars formed at the same time, in a single burst, and are now evolving together. But coordinated bursts like this are rare. Star formation is usually continuous. Gas collapses. Stars form. Some massive stars die and trigger the collapse of more gas. More stars form. It is an ongoing process. To shut it off completely, then restart it all at once, requires a trigger. A galaxy merger, a collision, an infall of gas, something dramatic. And this needs to happen in a galaxy at redshift 7, in the early universe, where galaxies are small, where mergers should be common, but coordinated bursts should still be rare. Yet James Webb is finding galaxies with these unusual stellar populations everywhere. There is also the problem of stellar ages. When you measure the age of stars in a galaxy, you use stellar evolution models. You look at the color and brightness of the stars. You compare them to models of how stars evolve. You infer how long the stars have been burning. But stellar evolution models depend on metallicity. A star with high metallicity evolves differently than a star with low metallicity. Metals affect the opacity of the star's interior. They affect how energy is transported from the core to the surface. They affect the star's lifetime. If you get the metallicity wrong, you get the age wrong. And we are now realizing that metallicity in the early universe is more complicated than we thought. It is not uniform, it is patchy. Some regions are enriched, some are pristine, some are partially enriched. When you look at a high redshift galaxy and measure its stellar population age, you are assuming a metallicity. You are plugging in a number. But what if that number is wrong? What if the metallicity is higher or lower than you assumed? Then the age you calculate is wrong. And if the ages are wrong, then the timeline of galaxy formation is wrong. James Webb is now forcing us to confront this, because it is measuring metallicities directly, and the metallicities do not match what we assumed. Which means the ages we calculated are wrong, which means the models are wrong. And if the stellar population models are wrong, then everything downstream is wrong. Star formation histories, galaxy mass estimates, chemical evolution tracks, the entire framework we use to interpret galaxy observations. We are not just refining the models, we are questioning whether the models are salvageable. There is another phenomenon that James Webb has revealed, and it concerns the nature of dark matter itself, not whether dark matter exists. That is well established. But what dark matter is made of and how it behaves. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all. The only way we detect dark matter is through its gravitational influence. It bends space-time. It pulls on galaxies. It creates gravitational lenses, bending the paths of light from distant objects. Gravitational lensing is one of our most powerful tools for mapping dark matter. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity of that object bends the light. The distant galaxy appears distorted, stretched into arcs, or even multiple images. By measuring these distortions, we can calculate the mass of the lensing object. And when we do, we find that the mass is far greater than the visible matter alone. The difference is dark matter. James Webb has observed some of the most distant gravitational lenses ever detected. Lenses at redshift 2, redshift 3, redshift 4, and the lensing signals are stronger than they should be. When you model a gravitational lens, you need to account for the mass distribution of the lensing object. Most of the mass is dark matter, concentrated in a halo around the galaxy. The distribution of dark matter follows a predictable profile: dense in the center, less dense farther out. This is called the Navarro-Frank-White profile, or NFW profile. It is based on simulations of dark matter structure formation. And it works. It explains lensing observations in the local universe. But when James Webb measures lensing at high redshift, the NFW profile does not fit. The dark matter distribution is more concentrated than it should be. The centers of dark matter halos are denser than simulations predict. This is called the core cusp problem, but in reverse. The traditional core cusp problem is that simulations predict dark matter halos should have a cusp, a sharp peak in density at the center. But observations of nearby dwarf galaxies show cores, flat density profiles at the center. Dark matter appears less concentrated than simulations predict. James Webb is showing the opposite problem at high redshift. Dark matter is more concentrated than simulations predict, which means either the simulations are wrong, or dark matter behaves differently at high redshift than it does now. If dark matter is more concentrated in the early universe, what caused it to spread out over time? Dark matter does not interact with itself. It does not collide, it does not scatter. It just falls under gravity. Once a dark matter halo forms, its density profile should remain stable. It should not change unless the galaxy undergoes a major merger or some other violent event. But if every high redshift galaxy shows over-concentrated dark matter, then something systematic is happening. Some process is affecting all dark matter halos in the early universe. One possibility is that dark matter self-interacts weakly, not enough to be detected in the local universe, but enough to matter in the dense environments of the early universe. If dark matter particles scatter off each other, even rarely, they could redistribute mass. They could smooth out cusps, or create cusps, depending on the interaction cross-section. But self-interacting dark matter has its own problems. If dark matter self-interacts, it should also interact with normal matter, at least gravitationally. And we should see evidence of this in the Bullet Cluster, two galaxy clusters that collided and passed through each other. In the Bullet Cluster, the dark matter and normal matter separated cleanly, proving that dark matter does not interact with normal matter beyond gravity. If dark matter self-interacts, we would expect the dark matter halos to have slowed down or distorted during the collision. They did not. Another possibility is that dark matter is not cold. Cold dark matter, CDM, means the particles are moving slowly, non-relativistic. They clump efficiently under gravity. But what if dark matter is warm? Warm dark matter particles move faster. They have more kinetic energy. This would suppress small-scale structure. It would prevent dark matter from clumping too tightly. Warm dark matter could explain why dark matter halos at high redshift are less cuspy than cold dark matter predicts. But warm dark matter creates other problems. It suppresses the formation of small galaxies, dwarf galaxies. And we observe plenty of dwarf galaxies. They are common, ubiquitous. If dark matter were warm, there should be fewer dwarfs, so we are caught between observations. Local observations suggest dark matter is less concentrated than simulations predict. High redshift observations suggest dark matter is more concentrated. Both cannot be true unless dark matter is doing something strange, or the simulations are wrong. Dark matter simulations are incredibly complex. They track billions of particles over billions of years. They require assumptions about initial conditions, about cosmological parameters, about how dark matter interacts with gas. If any of these assumptions are wrong, the simulations will produce wrong results. But the simulations have been tested, validated. They reproduce the large-scale structure of the universe. They match observations of galaxy clustering. They explain the cosmic microwave background. They work everywhere except at the smallest scales and the highest redshifts. And now James Webb is showing us that they fail there too. There is another dark matter anomaly, the abundance of satellite galaxies. Large galaxies like the Milky Way are surrounded by smaller satellite galaxies, dwarf galaxies orbiting the main galaxy. The Milky Way has dozens of known satellites. The Large Magellanic Cloud, the Small Magellanic Cloud, dozens of smaller dwarfs. According to dark matter simulations, the Milky Way should have hundreds of satellites, maybe thousands. Every clump of dark matter should form a dwarf galaxy. But we only see dozens. This is called the missing satellites problem. The standard explanation is that most of the dark matter clumps did not form stars. They remained dark, invisible. We cannot see them because they contain no visible matter. Only the largest clumps, the ones with enough gravity to hold onto gas despite radiation pressure and supernova feedback, formed stars and became visible satellites. This explanation works. It explains the missing satellites, but it predicts that the satellites we do see should be embedded in massive dark matter halos. The visible stars should only be a tiny fraction of the total mass. The rest should be dark matter. James Webb has now measured the dynamics of some high redshift dwarf galaxies. Galaxies orbiting larger galaxies at redshift 2, redshift 3. By measuring their velocities, their orbital speeds, we can infer their masses. And the masses are too low. The visible stars account for most of the mass. There is very little dark matter. These dwarf galaxies are not embedded in massive dark matter halos like they should be. They are mostly normal matter. How is this possible? If a dwarf galaxy does not have a dark matter halo, how did it form? Dark matter provides the gravitational well that allows normal matter to collapse. Without dark matter, normal matter would disperse. It would not form a galaxy. One possibility is that these are tidal dwarfs. Dwarf galaxies formed not from dark matter halos, but from tidal debris. When two galaxies collide, tidal forces can rip out streams of stars and gas. These streams can condense into dwarf galaxies. Tidal dwarfs contain little dark matter because they formed from material that was already in a galaxy, material that was mostly normal matter. But tidal dwarfs are rare in the local universe. They are short-lived. Without dark matter to hold them together, they disperse over time. Yet, James Webb is finding these low-mass, dark matter-deficient dwarfs everywhere at high redshift. If they are tidal dwarfs, then galaxy collisions were far more common in the early universe than we thought. And if they are not tidal dwarfs, then we do not know what they are. Another possibility is that dark matter has been ejected from these galaxies. Some process removed the dark matter, leaving behind only the stars and gas. But what process could do that? Dark matter does not interact. You cannot blow it away with supernova. You cannot heat it. You cannot push it with radiation pressure. The only way to remove dark matter is gravitationally. A close encounter with another galaxy could strip away the outer parts of a dark matter halo. But that would also strip away stars. And these dwarf galaxies appear intact, not tidally disrupted. So we have dwarf galaxies that should not exist. Galaxies with too little dark matter. Galaxies that violate the relationship between visible matter and dark matter. And we do not know how they formed. Now let me take you to a cosmological problem that cuts even deeper. The problem of initial conditions. The universe, as far as we can tell, began in a state of extremely high density and temperature. The Big Bang. From that initial state, the universe expanded and cooled. Protons and neutrons formed. Atoms formed. Structures formed. Everything we see today emerged from those initial conditions. But what were those initial conditions? Why did the universe start in that particular state? Why was it so uniform, so smooth, with only tiny density fluctuations? The answer, according to standard cosmology, is inflation. A brief period, in the first fraction of a second after the Big Bang, when the universe expanded exponentially, faster than light. This rapid expansion stretched quantum fluctuations to cosmic scales, creating the density fluctuations that eventually became galaxies. It also smoothed out the universe, making it uniform on large scales. Inflation solves many problems. It explains why the universe is flat, why it is homogeneous, why the cosmic microwave background has the temperature fluctuations it does. Inflation is a cornerstone of cosmology. But inflation is also speculative. We have never observed it directly, we infer it from its predictions. And recently, some of those predictions have come into tension with observations. Inflation predicts a specific spectrum of density fluctuations. A power law. Small fluctuations on small scales. Larger fluctuations on larger scales. This spectrum is written into the cosmic microwave background. And it matches observations beautifully. But inflation also predicts the amplitude of these fluctuations. How strong they are. and the amplitude affects how quickly structure forms. Stronger fluctuations mean faster structure formation. Weaker fluctuations mean slower structure formation. The cosmic microwave background measures the amplitude of fluctuations at the time the CMB was emitted, 380,000 years after the Big Bang. By plugging this amplitude into lambda CDM, we can predict how much structure should have formed by any later time. By 1 billion years. By 5 billion years. By 13 billion years. And the prediction is that structure formation should have been gradual. Small structures first, larger structures later. Galaxies forming slowly over hundreds of millions of years. But James Webb is showing us massive galaxies, massive black holes, massive structures, all existing far too early, which means either the amplitude of fluctuations was higher than the CMB suggests, or structure formation was more efficient than lambda CDM predicts, or inflation did not happen the way we think it did. If the amplitude was higher, why does the CMB not show it? The CMB is a direct snapshot of the universe at 380,000 years. The fluctuations are right there. We can measure them. They are not stronger than expected. They match the lambda CDM prediction, unless the CMB is lying, not literally. But unless there is some systematic error in how we interpret the CMB, some foreground contamination, some unknown effect that is biasing our measurements. Multiple teams have analyzed the CMB data. Planck, WMAP, ACT, SPT. All of them agree. The fluctuations are what they are. If structure formation was more efficient, what made it efficient? The physics of gravitational collapse should be universal. Gas collapses under gravity at the rate gravity allows. You cannot make it collapse faster without changing gravity itself, unless there was more matter. If the density of the universe in the early epochs was higher than we thought, structure would form faster. But the density of the universe is constrained by multiple observations: the expansion rate, the abundance of light elements, the cosmic microwave background. All of these measurements agree on the density. There is no room for significantly more matter, or inflation happened differently. Not a single smooth exponential expansion, but something more complex, multiple phases, oscillations, variations in the expansion rate. This could create different patterns of density fluctuations. Stronger fluctuations in some regions, weaker in others. Some theorists have proposed models of non-standard inflation, warm inflation, hybrid inflation, multi-field inflation. Each model produces slightly different predictions. But none of them are well tested, and none of them clearly explain the James Webb observations without creating new problems elsewhere. The deeper issue is this. Inflation is based on quantum field theory. It assumes a scalar field, the inflaton field, underwent a phase transition. The energy of this field drove the exponential expansion. Then the field decayed, reheating the universe, producing the matter and radiation we observe today. But we have never detected the inflaton field. We have never observed a scalar field behaving the way inflation requires. It is a hypothesis, a well-motivated hypothesis, a hypothesis that solves many problems, but still a hypothesis. And now James Webb is showing us that the predictions of inflation, when combined with lambda CDM, do not match the universe we observe. Which means either inflation is wrong or lambda CDM is wrong, or both are incomplete. There is one more anomaly I need to tell you about. It is subtle. It concerns the nature of the vacuum itself. In quantum field theory, the vacuum is not empty. It seethes with virtual particles. Particle-antiparticle pairs constantly pop into existence and annihilate. This is called vacuum energy. And vacuum energy has a measurable effect. It contributes to the cosmological constant, the energy density of empty space, what we call dark energy. The problem is that when you calculate the vacuum energy using quantum field theory, you get a value that is 10 to the power of 120 times larger than the observed dark energy density. This is called the cosmological constant problem. It is one of the greatest unsolved problems in physics. The discrepancy is so enormous that most physicists assume there must be some mechanism that cancels out most of the vacuum energy. Some symmetry, some unknown physics, leaving only the tiny residual that we observe as dark energy. But what if the vacuum energy is not constant? What if it changes over time? This would be dynamical dark energy. Not a cosmological constant, but a field that evolves. Some models propose quintessence, a scalar field, similar to the inflaton, but active in the present universe. The energy density of this field changes as the universe expands. Early in cosmic history, the field had one value. Now it has a different value. In the far future, it will have yet another value. If dark energy is dynamical, it affects the expansion rate. And if the expansion rate changes over time in ways lambda CDM does not account for, it affects distance measurements. It affects the timeline of cosmic history. It affects when galaxies could have formed. James Webb is measuring distances to high redshift galaxies using standard candles and spectroscopy. These distances depend on assumptions about the expansion history. If dark energy was different in the past, the distances are wrong. And if the distances are wrong, the redshifts correspond to different times. The galaxies might be older than we think, or younger. Some teams have reanalyzed James Webb data assuming dynamical dark energy. And the results are intriguing. If dark energy was slightly stronger in the early universe, it would have accelerated the expansion more. This would give structure more time to form. Galaxies would be older than their redshifts suggest. The timing problems go away, but dynamical dark energy creates its own problems. If dark energy was stronger in the past, why is it weaker now? What mechanism caused it to decrease? And why did it decrease at the rate it did? The timing seems fine-tuned, as if the universe adjusted dark energy specifically to allow galaxies to form when they did. Fine-tuning is a red flag in physics. When a model requires parameters to be set to very specific values for no apparent reason, it suggests the model is incomplete. There should be a deeper explanation for why the parameters have the values they do. Some physicists invoke the anthropic principle. We observe the universe we observe because if the parameters were different, we would not exist to observe it. In a multiverse with infinite universes, all possible parameter values exist somewhere. We happen to be in a universe where the parameters allow life. This is not an explanation. It is an observation, and it is deeply unsatisfying. Others propose that the parameters are not fine-tuned at all. They are natural outcomes of some deeper theory, string theory, loop quantum gravity, some framework that predicts the values of dark energy, dark matter density, the expansion rate, all from first principles. But we do not have such a theory yet. String theory has made no testable predictions. Loop quantum gravity is incomplete. We are groping in the dark. And meanwhile, James Webb keeps observing, keeps finding galaxies that should not exist, structures that should not have formed, black holes that should not have grown, chemistry that should not be present. Every new observation is a nail in the coffin of lambda CDM. Let me bring this back to what it means. Not just for cosmology, for reality itself. When Copernicus proposed that the Earth orbits the Sun, It was not just a change in astronomy, it was a change in how humans saw themselves. We were not at the center. We were not special. We were one planet among many, orbiting an ordinary star. When Hubble discovered that galaxies are receding from us, that the universe is expanding, it was not just a measurement. It was a revelation. The universe had a beginning. It is finite in age. Time itself had a starting point. When we discovered dark matter and dark energy, it was not just surprising. It was humbling. 95% of the universe is made of things we do not understand. We are not just peripheral. We are ignorant. And now, James Webb is showing us that even the 5% we thought we understood, we do not. The timeline of cosmic history is wrong. The formation of galaxies is wrong. The growth of black holes is wrong. The chemistry of the universe is wrong. The distribution of dark matter is wrong. We are not refining our knowledge. We are discovering that our knowledge was an illusion. A house built on sand. It looked solid. It felt solid. And now the ground is shifting beneath it. This is not a crisis in cosmology. This is a crisis in epistemology. How do we know what we know? How confident can we be in our models when every time we look closer they break? There is a concept in science called a paradigm shift. The term was coined by philosopher Thomas Kuhn in 1962. A paradigm is the framework within which science operates. The set of assumptions, methods, and theories that define how we interpret observations. For most of scientific history, progress happens within a paradigm. We make measurements. We refine theories. We add details. The paradigm holds. But occasionally, observations accumulate that the paradigm cannot explain. Anomalies. At first, they are dismissed as experimental error. Then they are treated as edge cases, outliers that do not affect the core model. But eventually, the anomalies become too numerous, too significant. The paradigm cracks, and science undergoes a revolution, a paradigm shift. The shift from geocentrism to heliocentrism. The shift from classical mechanics to quantum mechanics. The shift from static universe to expanding universe. Each time, the old framework was not just modified, it was replaced. And with it, our entire understanding of reality changed. James Webb is pushing us toward another paradigm shift, and we do not know what the new paradigm will be. Some scientists are proposing tweaks, adjustments to lambda CDM. Maybe dark matter is slightly warmer than we thought. Maybe the initial fluctuations were slightly larger. Maybe star formation was slightly more efficient. Tweaks, patches, band-aids on a framework that is hemorrhaging. But other scientists are going further. They are questioning the foundations. Is general relativity correct? Is the cosmological principle valid? Is the universe homogeneous and isotropic? Or are we in a special location? Is time itself flowing at the rate we think it is? Some have proposed that the speed of light was different in the early universe. Faster. This would allow information, energy, and structure to propagate more quickly, solving the horizon problem and the structure formation problem. But changing the speed of light breaks everything. Every physical constant is connected. If you change one, you have to change all of them. And we have no mechanism that would cause the speed of light to vary. Others have proposed that gravity was stronger in the early universe. Stronger gravity would allow structures to collapse faster, forming galaxies and black holes more quickly. But gravity is described by general relativity. The equations are fixed. You cannot make gravity stronger without changing the equations. And if you change the equations, you break all the other predictions that general relativity makes correctly. GPS. Gravitational waves. Orbital mechanics. All of it depends on general relativity being exactly what it is. Still, others have proposed that time itself flowed differently in the early universe. that the rate of physical processes was faster. This is called varying speed of light cosmology, or VSL. It is fringe, it is speculative, but it is being taken seriously because the mainstream explanations are failing. There is a more disturbing possibility: that the universe is not comprehensible, that the laws of physics we have discovered apply only to a limited domain, our local region, our current epoch, and beyond that domain, the rules change, not gradually, abruptly. The universe is not governed by universal laws. It is a patchwork. Different regions operating under different physics. This would explain why the early universe looks so different from the present universe. Not because it evolved according to laws we understand, but because it operated under different laws entirely. And if that is true, then cosmology is not physics, it is cartography. We are not discovering universal principles. We are mapping local conditions. And beyond the map, there be dragons. This is not science fiction. This is where the data is leading us. When every observation defies the model, when every prediction fails, you have to consider that the model is not just incomplete. It is inapplicable. You are using the wrong framework entirely. And if we are using the wrong framework, then what does that say about everything else we think we know? If cosmology is wrong, is particle physics wrong? If general relativity fails at cosmic scales, does it fail elsewhere? What about quantum mechanics? What about thermodynamics? The foundations of physics are interconnected. You cannot pull one stone out without the other shifting. And right now, James Webb is pulling out the stone labeled lambda CDM, and the entire structure is trembling. Let me tell you what the scientists are not saying publicly. Not in press releases, not in interviews, but what they are saying in private conversations, in emails, in conference hallways after the sessions end. They are saying they do not understand what they are looking at. They are saying the models are broken beyond repair. They are saying they need new physics, not modifications, new physics. And they do not know what that physics is. They do not even know where to start looking for it. Some are frustrated, angry even. They spent their careers mastering lambda CDM. They built simulations. They wrote papers. They won grants and tenure and awards. And now they are being told that all of it was based on a foundation that is crumbling. Their work is not wrong exactly, but it is incomplete to the point of being misleading. Others are excited. This is what they signed up for. This is why they became scientists. To be at the frontier, to see the map redrawn in real time, to witness a revolution. These are the ones proposing wild ideas. Testable ideas, they hope. Ideas that might lead somewhere. But many are simply bewildered. They look at the James Webb data and they do not know what to make of it. Every galaxy is an anomaly. Every black hole is a puzzle. Every measurement contradicts something else. It is like trying to assemble a jigsaw puzzle where the pieces do not fit. You can force them together, but the picture does not make sense. And you start to wonder if maybe these pieces belong to different puzzles entirely. There is a term in philosophy, epistemological crisis. It describes a state where you realize that your framework for understanding reality is inadequate. Not just incomplete, inadequate. You are standing in a room and you thought you understood the room. 4 walls, a ceiling, a floor. But then you notice cracks in the walls. And you peer through the cracks. And you realize the walls are not walls, they are curtains. And beyond the curtains is something vast and incomprehensible. And you do not know if you are in a room at all. You do not know what you are in. That is where cosmology is right now. Peering through the cracks. Seeing something beyond. And not understanding what it means. Now let me bring this back to you. Because this is not just an abstract problem for scientists and universities. This is a problem about reality. The reality you inhabit. You are made of atoms. Those atoms were forged in stars. Stars that formed in galaxies. Galaxies that condensed from dark matter halos. Dark matter that clumped under gravity. Gravity that followed the equations of general relativity. All of this happening in a universe that expanded from the Big Bang, according to Lambda CDM. That is the story you have been told. That is the story I have been telling you, the story we all believed. The atoms in your body are billions of years old. They have been recycled through multiple generations of stars. You are made of stardust. It is poetic. It is beautiful. It is the foundation of your identity as a physical being in a physical universe. But if the story is wrong, if galaxies did not form the way we thought, if stars did not evolve the way we thought, if the timeline is wrong, if the chemistry is wrong, then what does that mean for you? It means the atoms in your body have a different history than you were told. A history we do not understand. The carbon in your cells, the oxygen in your lungs, the calcium in your bones, all of it came from somewhere. Some process in some star, in some galaxy at some time. But if the galaxies are wrong, if the stars are wrong, then the process is wrong. And the story of your atomic ancestry is wrong. This is not pedantic, this is not academic, this is about the narrative of your existence, where you came from, how you came to be, what you are made of. And the answer is, we do not know, not anymore. You are listening to this right now. Photons are hitting your retinas, or sound waves are vibrating your eardrums, depending on how you are experiencing this. Those photons, those waves, they travel through space. Space that is expanding. Space that is filled with dark energy that we do not understand. The expansion of space is accelerating. This was discovered in 1998. It won the Nobel Prize. It is one of the most well-established facts in cosmology. But we do not know why. We call it dark energy, we measure its density, we observe its effects, but we do not know what it is. And if we do not know what dark energy is, how can we be sure it is constant? How can we be sure it will continue behaving the way it currently behaves? What if dark energy is not a constant property of space, but a dynamical field that is evolving? What if, at some point in the future, it changes? Not gradually. Suddenly. There is a hypothetical scenario called vacuum decay. It is based on quantum field theory. The idea is that the vacuum, the lowest energy state of space, might not be truly stable, it might be metastable, a false vacuum, like a ball sitting in a shallow depression on a hillside. The ball is stable, it is not rolling. But if something disturbs it, if there is a quantum fluctuation, the ball could roll down the hill into a deeper depression, a true vacuum. If the vacuum of our universe is metastable, then at any moment, a quantum fluctuation could trigger a phase transition. A bubble of true vacuum would form. Inside the bubble, the laws of physics would be different. Different values for the fundamental constants, different particles, different forces, and the bubble would expand at the speed of light, consuming the universe, rewriting physics as it goes. Outside the bubble, the universe continues as normal. Galaxies, stars, you. Inside the bubble, nothing survives. Atoms would not be stable. Matter as we know it could not exist. It would be a wall of annihilation sweeping through space at light speed. And because it moves at light speed, you would not see it coming. One moment you exist. The next moment, you and everything around you cease to exist. Not destroyed, rewritten. This is not science fiction. This is a legitimate prediction of quantum field theory. And we do not know if it will happen. We do not know if the vacuum is stable or metastable. We calculate probabilities. We estimate tunneling rates. And the probabilities are low. Extremely low, but not zero. Never zero. And if James Webb is showing us that the universe does not follow the laws we thought it did, if the early universe operated under different physics, then how confident can we be that the vacuum is stable? How confident can we be that the rules will not change? You might think this is fear-mongering, alarmism, but it is not. It is simply acknowledging the depth of our ignorance. For decades, we thought we understood the universe. Approximately, mostly. Sure, there were mysteries, dark matter, dark energy, quantum gravity. But the framework held. Lambda CDM worked. General relativity worked. The standard model of particle physics worked. We had a coherent picture. James Webb has shattered that picture. Not by revealing something new, by revealing that what we thought we knew was wrong. And when the foundation is wrong, everything built on it is suspect. There is a psychological phenomenon called the illusion of knowledge. It is the belief that you understand something when you do not. You have learned the words, you can recite the facts, you can pass the test, but you do not actually comprehend the underlying reality. You have memorized a map, but you have never visited the territory. Humanity has been operating under the illusion of knowledge about the universe. We thought we had the map. Lambda CDM, dark matter, dark energy, the Big Bang, inflation, galaxy formation, stellar evolution. We had the story, we told it confidently, we taught it in schools, we wrote it in textbooks. And now we are realizing we never had the map. We had a sketch, a cartoon, a simplified model that worked in certain regimes but failed catastrophically when we looked closer. This is terrifying. Not because the universe is dangerous. The universe has always been dangerous. Vacuum decay, gamma ray bursts, asteroid impacts, supernovae, black holes. The universe is filled with mechanisms of annihilation. But we thought we understood them. We thought we could predict them. We thought we had time to see them coming. Now we do not know. If the models are wrong, the predictions are wrong. If the timeline is wrong, the estimates are wrong. If the physics is wrong, everything is wrong. And you cannot escape this by ignoring it. You cannot opt out of living in a universe you do not understand. You are here. You are part of this. The atoms in your body are governed by these laws, whatever they actually are. The space around you is expanding, driven by forces we do not comprehend. The vacuum beneath your feet could be unstable, and there is nothing you can do about it. You are at the mercy of a cosmos that we thought we understood and now realize we do not. Let me tell you the final implication, the one that keeps me awake. Science progresses by making predictions. You develop a theory. The theory makes predictions. You test the predictions. If the predictions are correct, the theory is supported. If the predictions are wrong, the theory is falsified. This is the scientific method. It works. It has given us technology, medicine, engineering, everything modern civilization is built on. But the scientific method assumes that the universe is comprehensible, that it follows rules, universal rules, rules that apply everywhere at all times and all conditions. If you drop a ball on Earth, it falls. If you drop a ball on Mars, it falls. If you drop a ball in the Andromeda galaxy, it falls. Gravity is universal. But what if it is not? What if the universe is not universal? What if different regions, different epochs operate under different rules? Then prediction becomes impossible. You cannot extrapolate from one domain to another. You cannot test theories because the tests only apply locally. Science becomes limited, not just incomplete. Limited. James Webb is hinting at this possibility. The early universe does not behave like the present universe. Not just because it is younger, but because the rules might be different. Galaxy formation proceeds faster. Black holes grow larger. Stars form more efficiently. Dust accumulates more quickly. Dark matter distributes itself differently. None of this should happen if the laws of physics are universal and constant. So either the laws are not universal or they are not constant. Either space changes the rules or time changes the rules. Either way, the assumption underlying all of science is violated. And if that assumption is violated, then what is science? What are we doing? Are we discovering truth about the universe, or are we just describing local regularities? Are we physicists, or are we historians recording what happened to happen in this particular region of space-time? This is not a trivial distinction. If science is the discovery of universal truth, then it is the highest achievement of human cognition. We have transcended our local experience. We have understood something fundamental about reality. We have touched the eternal. But if science is just local description, then it is anthropology. We are studying the customs of this particular region of the universe. And those customs might not apply elsewhere. We are not discovering truth. We are mapping our neighborhood. And beyond our neighborhood, we know nothing. Some physicists are beginning to whisper this, not in public, not on record, but in private. They are beginning to ask, is the universe comprehensible at all? Or is comprehensibility itself an illusion? A local property of this region of space-time, where the laws happen to be stable enough and simple enough for intelligent beings to evolve and develop science? In other regions, in other epochs, maybe the laws are too chaotic, too complex, too rapidly changing. Intelligence could not evolve there because there is no stable substrate, no predictable environment, no evolutionary pressure toward understanding because there is nothing stable to understand. We are here, in this place, at this time, because the laws here and now are comprehensible. We are selected for comprehensibility, not because the universe is comprehensible, but because only in comprehensible regions can beings like us exist to ask the question. This is a kind of anthropic principle, not about the fine-tuning of constants, but about the fine-tuning of comprehensibility itself. And if this is true, then we are not discovering universal laws. We are discovering the local conditions that allowed us to exist in the first place. We are reading our own origin story and mistaking it for the story of everything. James Webb is showing us the edge of comprehensibility, the early universe, where the rules we understand do not apply. And beyond that edge, we do not know what lies. More incomprehensibility? Different laws? Chaos? Or something we cannot even conceptualize because we do not have the cognitive framework to conceive it. You are hearing this, and maybe you think I am overstating it. Maybe you think the scientists will figure it out. They always do. Every anomaly eventually gets explained. Every mystery eventually yields to investigation. Progress continues. But that is the illusion of knowledge speaking. The assumption that because science has succeeded before, it will succeed again. The assumption that every mystery has a solution. The assumption that the universe is ultimately knowable. What if it is not? What if James Webb has found the boundary? The limit of human knowledge? Not because we are not smart enough, not because we do not have the right instruments, but because beyond that boundary, the universe simply does not conform to anything we would recognize as law. In the early universe, galaxies formed impossibly fast. Black holes grew impossibly large. Stars burned with impossible chemistry. Dust accumulated impossibly quickly. Structure emerged impossibly early. Every observation is an impossibility, piled on top of impossibilities. At some point, you have to stop calling them impossibilities and start calling them reality. The universe did what it did. We are the ones who are wrong. Our models are the impossibilities. Our predictions are the fantasies. Reality is what James Webb sees. And reality does not care what we think is possible. This is the final lesson, the humbling. We built Lambda CDM, we celebrated it, we called it the standard model of cosmology. We thought we had figured it out. We thought we understood the universe's history from the Big Bang to the present. We thought we could predict its future. And then we looked. With the most powerful telescope ever built, with an instrument designed to confirm our theories, and instead it revealed that we were wrong. Not slightly wrong, fundamentally wrong. And we still do not know what we are wrong about. Gravity, dark matter, expansion, time itself? The universe is not what we thought. And maybe it is not what we can think. Maybe the framework required to understand it is beyond human cognition. Maybe we are like ants trying to understand calculus. The concepts do not fit in our brains. The patterns are too complex. The relationships too abstract. Or maybe we just need time. Time to develop new mathematics, new models, new ways of thinking. Maybe a genius will come along and see the pattern, write down the equation, solve the mystery. And future generations will look back on this era and wonder how we could have been so blind. But right now, in this moment, we are blind. We are staring at data we cannot interpret, observations we cannot reconcile, anomalies we cannot explain. We are lost in a universe we thought we knew. And the map has dissolved in our hands. You wanted to understand the cosmos. You wanted to know where you came from, what you are made of, where you are going. And the answer James Webb gives you is this: we do not know. We thought we knew, but we were wrong. The atoms in your body came from stars. That much is still true. But the stars formed in ways we do not understand, in galaxies that should not exist, under conditions we cannot model. Your atomic ancestry is a mystery. Your origin is unknown. The space you occupy is expanding. But the rate is wrong. The mechanism is unclear. The future is unpredictable. You are standing on a foundation that is shifting, and you cannot see what it is shifting toward. The universe is 10 billion years older than you. It will outlive you by trillions of years. You are an infinitesimal flicker in an incomprehensible expanse. And even that incomprehensible expanse, it turns out, is more incomprehensible than we thought. This is not comforting. This is not inspiring. This is not the uplifting cosmos of popular science. This is the real cosmos, the one James Webb sees. The one that does not conform to human expectations. The one that does not care if you understand it or not. You are here, in this universe, for a brief moment. And during that moment, the universe is revealing to you that it is stranger, more alien, more incomprehensible than any story we told ourselves. We thought we were close to understanding. We were not close. We were barely at the beginning. And the beginning is already impossible. So here is what you do with that knowledge. You could despair. You could conclude that if we do not understand the universe, there is no point in trying, no point in learning, no point in asking questions. Or you could marvel. You could recognize that you are alive at a moment when the map is being redrawn, when the foundations are being questioned, when the frontier is opening. You are witnessing a paradigm shift in real time. You are seeing the moment when human knowledge hits the wall and has to decide whether to break through or build a new wall somewhere else. The universe is not obligated to make sense to you. It owes you nothing. Not comfort, not comprehension, not meaning. It simply is. And you, through no choice of your own, are part of it. James Webb has shown us the anomalies, the impossibilities, the cracks in the model. And those cracks are growing. And through those cracks, we see something vast. Something that was always there, but we could not see because we were looking through the lens of a theory that was inadequate. The theory is breaking, the lens is shattering, and beyond it, the universe waits. Indifferent, incomprehensible, real. That is what James Webb has given us. Not answers, questions, not certainty, doubt. Not a map. A warning that the territory is larger and stranger than any map could contain. And now you know. The universe is not what you thought. The cosmos is broken, not literally, but our understanding of it is, and we do not know how to fix it. If you found this disturbing, good. Reality should disturb you. If you want to see more attempts to make sense of the incomprehensible, if you want to follow the unraveling in real time, subscribe. Hit the notification bell, because this story is not over. James Webb is still observing, still finding anomalies, still breaking models. And we are still here, watching, trying to understand, failing, and trying again, because that is what we do. That is what it means to be human in a universe that does not care if we understand it. We look anyway, we ask anyway, we search for patterns in the chaos, even if the patterns are not there, even if the chaos is all there is, we look, because we cannot help ourselves. Because curiosity is the curse that makes us human. And the blessing. The cosmos is vast, you are small. James Webb has reminded us of both. And neither truth is comforting, but both are real. And reality does not bend to comfort. It simply is. Now you know what the telescope found. Anomalies that should not exist. And a universe that does not care what should or should not be. It simply is what it is. And we are left to make sense of it, if we can. Good luck. You are going to need it.